And we are broadcasting live right now. Ken is joining me from Georgia, and I'm here in Rhode Island. And we have just released, less than a week ago, our debut for a new company that we are coming out with, HoverBrothers Incorporated, LLC. And that video is already taking off, and that video has currently over 100,000 views and is climbing fast. So it could very well top 1 million by the end of the month, and that would be really good for us to reach a lot of people with this. And the reviews have been mixed, and it's been interesting reading the comments and going through, and wanted to address most of the main questions that were being asked there and the main concerns, and sort of have an open Q&A where people could come and join and ask any question they want live, and sort of get to know us and where we're coming from and what we're doing. So I'll start with myself. My name is Jeremy Riss, and I'm from Southeastern Mass. I have a degree in physics from Bridgewater State University. It's a bachelor's degree. I basically been pursuing advanced research in my spare time into all things related to classified research, anti-gravity, invisibility technology, metamaterials, quasi-crystals, any kind of thing on advanced propulsion or anything remotely related to anti-gravity is basically been my main point of interest. And my other interests have been a lot of different types of physics, and mainly theoretical physics. I started getting into physics because I read a book by Richard Feynman in high school, and I've always sort of been into a lot of Feynman's work on quantum electrodynamics and path integrals and the Feynman diagrams and that sort of thing. I've always been interested in particle physics and a lot of these other more intricate theories of what's out there, and mainly this theory of everything. You know, what is the grand unified theory of everything? We've been chasing after this way to unify gravity. What is gravity? What is mass? What is energy? What are all these things that are yet undefined? I mean, we kind of learn about them in textbook physics in high school. You kind of learn to say what these things are, but even our top scientists don't really have perfect, accurate, bulletproof definitions for these things. And, you know, these are still unanswered questions in science, and I've been looking for a lot of those answers. And really liked one particular approach to this, and that's been like fractals and the idea of what was put forth with the Mandelbrot set and these other fractal sets with reiterating functions that produce really complex patterns over time, which is, again, what our universe is. It's a very complex fractal with a lot of symmetries and similarities that reoccur, but it's something different, and but similar. And Stephen Wolfram's book, A New Kind of Science, sort of led me down a path of researching generating algorithms or computational spaces that could be created, where really complex computational spaces could be created with very simple algorithms. And so I was doing a podcast back in the day on my channel talking about this, and that's when Mr. Ken Briggs called in and wanted to talk all about his physics and theories on science. And he had some really good insights on these theories of everything and some of these ideas and what this was all about. And I was like, wow, this guy really knows a lot. And that's how I met Ken and started talking to him, and we sort of formed a friendship through that. And we've been talking sort of in the background about a lot of different subjects for a number of years now. And recently we were talking about, as I started getting back into making YouTube videos and stuff, and talking with him, especially with what has gone on with this recent craze that's going on right now, that has everyone talking about with what Tom DeLonge's doing in the UFO disclosure that's happening in Washington, supposedly, and all this that's going on. And of course, I have my own interpretations of that, having researched this stuff for a long time, and kind of see through the higher reasons and larger reasons behind some of these things that I've pointed out and posted about on my channel. But really, it motivated me to say, you know what, these guys don't have it. They don't have anything. Like they have this channel that's devoid of, you know, like their website just has a little part of this aerospace company. It says two things, and they added beam propulsion and advanced electrogravitic propulsion to their website only after I pestered them for about a month about, like, why aren't you guys talking about Project Skyvault or Project Grasp or any of these other, like, classified anti-gravity research projects? If you're talking about disclosure and coming forward with all this information that the government's been working on, why aren't you talking about those things? So it kind of frustrated me that they're not doing anything real, and that I didn't see anything real going on there. And talking to Ken, which one of the things that me and Ken have been really talking about a lot lately is warp drive technology. And warp drive propulsion just dusts any other form of propulsion that you could possibly bring forth to the table or conceive of. Ion wind propulsion, any other propulsion that you can conceive out there. Go to the SpaceIF or STAFE2 conference where they have NASA holds, you know, basically DARPA's recruiting grounds for what they want to fund next in terms of advanced propulsion research and stuff like that. It's literally a conference for that, and you won't find anything, any ideas there in any of the literature there for the past many years on anything that's better than warp drive technology. Warp drive is the epitome. And with really what me and Ken presented, and I'll let Ken introduce himself in a second and give you some of his background. What we just presented is the key to warp drive technology. It's the negative energy states. It's what all these other groups lack. They haven't been able to figure out or understand. It's kind of been this missing gap that has held us back from creating warp drive technology. And what we've essentially done is just shown you that missing piece. And I hope we didn't reveal too much in some ways, but still, it's quite a puzzle to sort through. And what we've given people enough seems to be quite a bit for them to sort of sift through so far. So I'll go ahead and let Ken introduce himself, and then we'll talk more about the theory, where we're going with the company, and things like that.
Well, hey everybody. My name is Ken Briggs, and I have Jeremy and I have paired up in order to bring this sort of new way of defining our reality that is algorithmically efficient and mathematically simplistic, and yet produces the right answers. But this is a background. I grew up in Connecticut. I started doing physics by the 9th grade, and one of my high school professors eventually told me, hey, you know, it's one thing to try to recreate physics, but maybe you want to, as it were, learn physics first. And then once you figure it all out that way, then try to, you know, forge it ahead. So I've kind of lived with that nugget in my brain since that time. I attended Princeton as an undergraduate, and there I got a chance to talk with Professor White, who was over the math department, and then also got a chance to do my junior and senior research projects, even though I was an aerospace engineer, with the physics department. So Professor White put me in contact with Alexander A. Migdal, who was completely in line with all the things short of aerospace that I really wanted to pursue. And he started my grounding in what we call simplicial quantum gravity, or SQG. And SQG was one of the first mathematical approaches that tried to describe gravity from the ground up. And so under his tutelage, I learned a lot more about what I'd already been pondering for since high school, and was able to find a good mathematical niche to really build up my own ideas. And from that time period on, and finding that there, as time has gone on, there have been many elements that have come into the space of my universe that have allowed me to take it steps farther. You know, so one of those would be Lewis Kaufman. Another one, he's a not mathematician. Another one would be, I'm trying to think of his name here, from Stanford, Lenny Susskind, who I don't know personally, but he's been very good at putting out information on his research into entanglement and ER equals EPR. But in the end, I felt that I was really in a very unique place to be able to put a lot of these pieces together, and that actually occurred back at Princeton. But since then, I've also attended the University of Maryland. I've got my master's degree in physics, et cetera, et cetera, et cetera. I've worked at the Patent and Trademark Office. I've worked for the Department of Defense through Martin Marietta, blah, blah, blah. So I've been through a lot of different routes, and inevitably always circling back to getting this physics accomplished. And so we realized a long time ago that what we were really dealing with was entanglement. The approach that my earliest professor, Sasha Migdal, had was not considered entanglement at that point, but what we've realized since then is that's what we're really talking about. And so we were able to truly find the core of what Phoenix was all about, and that's why we named it Phoenix. But since then, we've just been pursuing how to not only discuss and describe the merits of Phoenix in terms of how does it actually talk about the strong nuclear force, how does it talk about gravity, how does it talk about the weak nuclear force, how does it talk about electromagnetism, how does it talk about quarks, how does it talk about leptons, how does it talk, maybe you see how the list of things is seemingly endless, but it's not. It's pretty finite, but it's, you know, how do we talk about the Planck scale, how do we talk about nuclear theory, how do we talk about chronodynamics, how do we talk about, and so Phoenix has basically created this umbrella theoretical structure by which to talk about all of these things in a way that is exactly consistent with what we've been measuring.
But it's different than what these other, you know, Gravity Research Foundation, for example, these other groups are doing is sort of a top-down approach, and this is a bottom-up approach where you're literally building off of vertices by finding these rules of it.
That's right. That's what makes this particular theory unique. It's unique because all of the other theories, including string theory, that really attempt to, I'm not going to say the all, let me say most of the other theories that attempt to describe reality are starting from the most general platform and then working their way down to see whether or not, you know, gravity exists within the manifold of the theory, whether or not certain forms of quantum gravity exist, or sorry, certain forms of quantum field theory exist within the confines of that larger structure. What we're able to demonstrate from the ground up is that with remarkably simple assumptions, we actually have a whole mathematical framework that's already there. And that mathematical framework then enables us to define these quantities like quarks or like electrons and positrons, and then to be able to get to what do we mean by photons, et cetera, and thus to derive where the quantum field theories come from. So why are we even talking about quantum field theories? But from that point, to then demonstrate how do you get to this other realm where we're talking about relativity theory, where we're talking about the speed of light being a constant, being constant in a vacuum, where we're talking about quantum gravity or gravity in general, and then to be able to build up to a universal platform.
Right, because I've always had that idea. This was an idea that came to me in high school, and it's been with me since high school. Was that quantum relativity basically could be thought of as like that Hall of Mirrors approach. That's how you could get relativity, or this infinite space, out of quantum, out of nothing. Is literally, if you put two mirrors together at the smallest level, you know, the tighter you put them together, it's just a infinite illusion into space. It's sort of what it creates. And I've always thought of it like that, but I've never been able to visualize it or actually put it into mathematics. And that's what you've done in the paper that's on the theory page on our website. And I think
that's right. In that, what we're attempting to do, Jeremy, thank you. Paper demonstrate how does one actually Einstein's special relativity theory from very simple combinatoric principles. And what we're laying the groundwork for are the next steps, which is, okay, we can derive special relativity theory on a combinatoric basis. We'll be showing in the next paper how to derive scattering theory or quantum field theory in the same combinatoric language, and then demonstrate how to generate general relativity theory or a quantum general relativity theory in combinatoric language. And through this process, also demonstrate where the language of Phoenix functionally fits in. You know, it's all combinatorics, but where those matrices that we're presenting in terms of the stuff that we've already told you, where those matrices actually fit in to this ground game. You know, so from those matrices, we can completely define quantum scattering theory, and thus completely define quantum field theory, and define, you know, quantum gravity, which is really the holy grail of modern physics. But, you know, when we get to that point in the third paper, we'll be demonstrating very clearly why it's actually not that difficult. But again, the approach that we took really from a ground up, as opposed to the top down approach.
And Raymond Bello has a good question here. He said, I'm curious if Ken ever did any practical Phoenix experiments validating the mathematical model. If so, what instrument did he use to create neutrons and such like? And I think really we're going off of a lot of the big experiments in physics, the big quantum experiments that are really difficult to explain and don't have a good theory to explain them. And that's what this theory explains. So I really, is that a good answer for that question, Ken?
Good answer. I would also say that how we understand nature, and this is a very critical point, I think, is that it is completely mathematical. Now, you know, someone's going to try to argue with that point, and I understand, but 400 years of physics has demonstrated to us that math is singularly the language that we can use to at least define measurement. And so how Phoenix sort of takes that understanding, as well as many other modern, you know, physics theories, is that let's find what the core of that math is. What is the core? What's actually going on at the most fundamental basic level of any of these theories that we have out there, of any of this mathematical language that we've used to construct these theories with. And if we can resolve at the core what's really going on, for example, in general relativity theory, we would say it's the general principle of covariance, or general covariance, is the core element that then gives rise to Einstein's theory of gravity.
Well, you know, Einstein, one of Einstein's most famous equations is that E equals mc squared equation, which I really thought was profound, because it literally says that mass is just energy that's trapped but traveling at the speed of light. And I've always thought of, like, well, how can energy be trapped? Is it, you know, is it trapped in a circle? Is it trapped? Well, how is the form that it takes when it becomes trapped? And, you know, how does it become trapped? And what does it look like?
Exactly.
And Phoenix theory has essentially done that with these particle graphs. And what they show is that literally energy sits on these vertexes, and it's trapped and bound to these vertexes with these certain matching rules. It has 3 degrees of freedom, and that's essentially what these graphs are showing. And the interesting thing about these graphs is that they're real easy to turn into matrices. You just figure out how many vertexes are in your graph, and so there's 2 in this graph. You have a 2x2 matrix, which will describe that, and you can populate the matrix quite easily by just asking, labeling each vertex 1 and 2, and then saying, well, in 1, 1, how is vertex 1 connected to itself? And it's connected to itself with 2 loops, so there's a 2 there. and then they're connected to each other with a 1, so it'd be 1 on either side. And I have this on the next page. So that's the matrix that you get for a neutrino, for this particle. And it's really easy to turn into a matrix, but what you find out is that when you put all these matrices together, right, that it starts producing a system that looks exactly like particle physics, which is remarkable. I'm
not sure, is everybody
sorry,
able to see what you've just done there?
Yeah, I was showing it on the camera, so it's essential.
Okay.
So they could see what I was showing. I have some of these graphs in front of me, and I was kind of showing them basically the basics of it, so they could kind of understand it. And again, we encourage you to go on and watch the videos that are on there. I know they're kind of they're not professionally done or anything, but you know, they're good videos. They're educational if you pay attention to what's going on and what he's doing, and he does the math out and how to do the matrix work for you. So
let me just quickly, in defense of the videos. The idea is that you're not really concerned about necessarily how I look or where I happen to be stationed. But what you're really concerned about, what am I telling you here?
yes.
That's really what I'm concerned about. You know, you're going to find, for example, when Nikola Tesla didn't really have a job anymore after he's kind of gotten booted out by Edison, that he had to work in it effectively on railroads. So I'm sure his living conditions weren't, you know, optimal.
Right. If you were to see him and like doing it, it's what's in there, right? I'm
not asking anyone to accommodate, as it were, the environment. All I want you to do is to think about the ideas. So if you can get into here, then we're good.
So, yes, exactly, and I think too many people get caught up about like my room and my conditions and what we're like broadcasting from, and they get distracted by that because literally, we put the last a decade or so of our lives into pursuing knowledge and pursuing information on this. I didn't, if I went and pursued work every day and then took a second job and made money, I probably could be living in my own place and have like really nice things and then be dressed up all fancy, not in a t-shirt, but it's about what's in here and what we know and our work ethic and capability. Like I have a job that I work on the side. I'm not going to quit my job just to start doing this or that, any of these ideas. I work for my money and I'm going to be working even harder.
Johannes Kepler, one of the people that I love. But Johannes Kepler, that was a very tragic person who had to live a very tragic life just to get those ideas somewhere, just to finally meet up with Tycho de Bry and actually get someone to freaking take measurements, right? But now we know, looking back all of these, hundreds of years, that Kepler had it. Mm-hmm. And it was Newton able to dig that information out of Kepler's logs and diaries, and then put it together to form what we call the theory of gravity. That's right. So the idea, at least, is that through his hardships, through his horrible life, through his, I can't make things ever meet because, I'm in the wrong town and now it's the Catholics and now it's the Protestants and I'm getting booted out and whipped around all the time. This is what the man went through. So the idea is that we still have what he really came up with. And Newton took that on and then developed the theory of gravity based on it. He was one of the giants that Newton so claimed that he stood on.
Right.
So we can't miss out on that. Most of the great things that are happening in our world are not necessarily happening at the top. They're not happening because there are, genius.
Even the things that happened in the past, it wasn't one of these big companies that was the ones that came out with the airplane. It was these two brothers in a bicycle company, working in their spare time to do this. So I mean, historically, revolutions do come from people like us, and you're not gonna. They don't come from groups like you know, the other ones, any of the others that you see out there, honestly. And you can check our math and what we're doing. We have something these other people don't. And, you know, we're not pushing.
And that was Da Vinci. So Da Vinci was effectively, you know, not well represented because his mother, I believe his mother was, she was married before. There was something going on in his life that allowed him not to be accepted by his society to even go to college. So all of the stuff that he developed, effectively, he had to do it outside of the academic community, outside of the clergy community. And that was a hardship. That was a huge hardship. But guess what? We know him today. Who else do you remember at that time? Not many other people, but we know Da Vinci. And that's what we're talking about. You know, I'm not saying that some misunderstanding that, but what we are saying is that in order for the ideas to get out, sometimes they're coming out from all of us.
All right, I want to get back to some of these questions too. Definitely a good, excellent point, because you know, people need to understand that about what's going on. I get all these comments are just people that are just so distracted. It's like, focus on the science, know what we're telling you, and these people are like, oh, this is bullshit. It's like, you haven't even looked at it. You haven't even taken the time to go through it or done one matrix application or one thing. Go through the graphs for the neutrons, see how it breaks down, see how it literally breaks down into the particles that give you the proton and give you these other particles, and go through some of these other interactions that you're familiar with, you know, common ones, and just go through them with the diagrams. There's a whole bunch. We've given you enough particles to start with that you should be able to, you know, model some simple interactions and be like, oh, wow, this works. Yeah, so I want to get back to some of these questions, the questions that I really want to address. Not going to be giving other people airtime that I don't think deserve it. So I won't mention some of these things that people are trying to throw on here. What do you mean? What do you plan by way of experiment for a proof of concept test? All right. So here's the deal: is I got a friend of mine. He's got a plasma physics lab, and we're yet to do a tour of it next week, and talk to him about a potential partnership to do some of our experiments there. But we're also currently seeking other partnerships, or maybe other laboratories that might have more up-to-date equipment. Because as far as he goes, he's not going to have. We're going to need to get a certain some lasers and some other things that we're going to have to order to do this experiment that he doesn't maybe have access to, that if we maybe partner with another lab that had these sort of things and had access to that, we might be able to save money and use existing, you know, lab equipment rather than having to go out and buy our own to do these experiments. So we're still open to other resources and potential partners out there, but we're still you know, going with what we have right now and who we know we can trust. So some of my friends that I've been working with and collaborating with for quite a while now. So yes, we're working towards that, and that really is going to need the funding mechanism, which is the next question. There's a lot of questions about that, which we're going to talk about right now and get that all squared away. Cryptocurrency. We currently have a Bitcoin wallet, and you know, I can put that out there if people want to send Bitcoin to that right now, and we're going to be setting that up in the future. I've heard about the idea of creating our own ICO, our own initial coin offering. We basically create our own cryptocurrency, like our own Bitcoin. And I don't really have the technical know-how to do that. And I don't trust anyone I don't know anyone that I could trust well enough that I could have them set that sort of thing up for us where I know I wouldn't get ripped off. So it's kind of hard to get something like that set up. I don't know how to do it myself, and I don't know if I would trust someone else to do that kind of a thing for me just because of what could happen. So it's kind of like I don't know what to do about that. So cryptocurrency, yeah, I dabbled in the Bitcoin thing. I actually won a competition for a couple of my older videos where someone gave me an award in Bitcoin, which I actually used to take a month off to get this whole company set up and get the website built and get the video put together and get all of this launched. So thank you to Greg out there. You know who you are for that. You've helped launch this or get it all set up. So yeah, and I don't know what's going to happen with its cryptocurrency. So unstable, it's volatile. It could crash tomorrow. I took a bunch of the money out to you know, pay for other things already out of Bitcoin when I saw it starting to fall again and go. I don't know what's going to happen with it, and it's too unstable for. We're not going to. Let's base our entire money in cryptocurrency, and then all the people that invest and and it's gone. Sorry, like I don't know what to tell you. All your money's gone. Yeah, I don't know what I do with that, and if we want to go full crypto, just because of what's going on with that right now. I don't know what's going to happen with it, whether outside forces are crashing it or whether it's going to crash on its own, or whether it's inside forces too. There's a lot of manipulation that seems to be going on with it, and not really something I trust at this point, or would trust with your money or my money. So again, your money's your money, and I don't spend your money. I'm saving it for everything we need to do. We did put down, we did drop $400 because the website went down and we overloaded it. We're going to need to get SSL certificate and a special type of hosting with expanded bandwidth. So I had to upgrade our hosting package, and that did cost $400. You know, it's a necessary expense to get everything else set up. Now, the funding platform, right now we have a donations platform. It's all we could put together at last minute. We wanted to get this thing launched on Christmas. We wanted to launch it on HoverBrothers Day, but we still had to get a lot of the stuff together and get everything put together. And we're still getting it set up. So please bear with us while we get the real initial this initial phase. Once we get the investment platform set up, we're going to have SEC filing. We need to get lawyers for this and everything. We need to file with the SEC and basically give them a number of stocks. We're going to give a price per stock, how many shares each of us own, so that we can maintain votes and ownership of the company, so someone can't just come in and buy us out and steal the whole thing. We have, you know, there's all kinds of things that have to go into it. It's a lot of thought, and I'm learning it now for the first time, and also doing it for the first time. So, you know, it's a lot of work, and we're hoping to get it all set up eventually, probably mid-January, end of January. Hopefully by February, we'll have the investment platform fully set up where people can invest. And at that point, I will be taking all the people that donated during that process and transferring those funds to actual stocks, and they'll be issued stock certificates once that's set up. In hindsight, I have a whole all those receipts saved and a whole list of everyone who's donated so far. And thank you. We've raised almost $2,000 actually. I think it just broke $2,000 because we just got a $500 donation from somebody, which is amazing. Thank you. That helps pay for all this stuff and get it all set up so that we can actually have a platform to do this off of. And again, Nikola Tesla, you know, couldn't have done this stuff just off the street. He needed a lot of help himself, and someone had to pay for his laboratory and his initial experiments. Someone who had to believe in him and think that, you know, well, this guy might actually have something here. It would be interesting. So, and we do have something, and I can't wait to share it with everyone and we're going through it the right way. Here, one of the things we wanted to address too was, oh, you're talking about open source, but you can't have patent and open source at the same time. And what's this? And you know, Ken actually worked at the patent office. He worked there for a while. He's very familiar with the patent office, and we're both very familiar with the patent office and how it's reacted to certain types of science within the scientific community, particularly with regards to cold fusion and cold fusion patents and devices. So no one in cold fusion can patent a device that they've created, even though this effect may or may not work. Not exactly sure. You know, there's too many scientists finding anomalous results and following this for it all to be correct science. Too many credible scientists, let me say. Not that numbers have any say in science or how many people follow something or believe something, but it's just the quality of their experiments and their data. It's something that can't really be denied at this point, especially with SPAWAR, the U.S. Navy's, you know, laboratories admitting that they have anomalous cold fusion experiment results. So, again, energy technology is also another part of what we want to pursue, and and look for with Phoenix theory and this new approach to particle physics, and how that might explain these strong nuclear force interactions and these Coulomb barrier breakings or tunnelings, so to speak, and how that actually occurs on the quantum level. So, but that's, oh man, there's so much that we want to do. We basically, the thing to get us started, though, is going to be that proof of concept. I mean, there's going to be a lot of people that aren't going to believe in this and aren't going to follow it, and we're going to need to show them that proof of concept, and that's really going to be our first goal, is to get that working and get that going, so that when we get a proof of concept and show people that first moment, hey, can you do this? That's when it's going to get real, and that's when the big donations are going to come in. And we're hoping that we can get these lasers, get the right laboratory. Of course, it's going to cost plane tickets and all kinds of other stuff, because Ken's going to have to fly from Georgia, and I'm going to have to fly from Boston probably, and go meet up and do these experiments. So it's relocation, maybe a couple months of living somewhere else, and those kind of things are going to have to be, and accommodations are going to have to be set up in advance, and we're going to have to rely on a lot of crowdsourcing and help in getting that all put together for the people who have the right kind of connections that want to be involved in this type of research and these types of breakthroughs. That's right.
The right type of connections, the right type of talent. So, we're looking for the computer science people. We're looking for the physicists. We're looking for the engineers in particular, who can help us to either run the experiments or to put together the laboratories and keep them under control. So there's a lot of talent that we're going to need in the process of being able to achieve these experiments. And we've already received applications, if you want to call them that, or at least people who want to help. And we're very, very thankful. We're going to get in contact with you and let you know how you can be of help to what we're trying to achieve.
Yes, we've gotten all the emails, and I'm going to be responding to people very shortly. Of course, we'll keep you updated with what's going on with the investment platform. We have a meeting scheduled for January 2nd with our advisors from LegalZoom, and we're going to see what they have to say about the next step forward with that process. So we're going forward with this. We're putting it together, and we're right on schedule to be putting this together. And I just want to thank you all for joining us and being here and asking these questions and stuff.
Thank you.
So yeah, cryptocurrency would never be a primary source of funding for us. We'd always want to have it as a backup that people could donate through crypto, and I might even post up a way for them to do that on the site shortly, maybe tonight after we finish this podcast. But yeah, I was hoping more questions about our theory. People seem to be asking us about other people and their theories. But
I mean, the people who have created our theory, right? And those people, we would love to also chat with them, maybe exchange ideas. They're coming. We can have a conversation, and be able to answer those types of questions once we feel like, and certainly when I feel like I'm really up to speed on these other ideas. My life has been really sequestered into development, and it's taken a lot out of me. So yeah, it's not sometimes easy to know all of the other things that have been going on in the theoretical landscape, but certainly I'm all ears, and I want to know. Just because I haven't studied it does not make it somehow magically not important. And I've realized that every step of the way in this creation of Phoenix. You know, basically information comes right on from field, and you're like, oh my God, I didn't really understand or know that. And then all of a sudden that blossomed the next phase of the work. So yeah.
Let's talk a little bit more about some of the really interesting and elegant parts of the theory, because I think people are really interested in that, and I'd like to maybe get into our theory a little bit so that people can understand it a little bit. Quantum entanglement, because everybody out there commenting, especially the people who think they know physics but don't really know physics, they're commenting saying that, you know, oh, that's not what quantum entanglement is. You guys don't know what quantum entanglement is. It's this thing with photons that the Chinese do with their satellites, and you know, it's this other thing. And well, what is that other thing? Let's talk about the spooky action at a distance, what Einstein called it, literally in that EPR paper where he was mocking the concept of it. The one thing that would be his undoing. I mean, it's the point where his theory fails. It covers everything else and explains everything else so greatly, but in this one area, it fails. Yeah. So, quantum entanglement. What's happening in these photons is that they get generated from the same photon. Is that they come from the same source point. And they're literally the same photon, right?
Oh, you mean for what Phoenix is saying, right?
What Phoenix is saying is that this is the same photon.
Phoenix is saying is that you've got these, what might otherwise be called these two energy vertices. Typically vertices that don't have loops or arrows, which means that they directly other vertices. They must connect to another vertex. But energy vertices, singularly, they're always paired up. Right? And that pairing up is what photons. Now, in all photons, those would be considered 2 photons. And that would be considered 4 photons, but that's 2 photons right there. Right? But the way Phoenix views it, the easiest manifest way of actually speaking about it is that no, it's actually a single photonic structure. It's a single. In that structure, you have what we would otherwise say, you've got these 2 possible vertices that might have properties in and of themselves, but they're entangled to each other.
Right, and the interesting thing is if you measure one, the other one's automatically down. So it literally, they're 2 halves of the same, or the opposite side of the same photon.
And so no matter where in the universe one vertex may appear, the other vertex may be somewhere else, they're still entangled. And what you really also have to conceive of is that in the Big Bang concept, right? Well, in the Big Bang,
I just wanted to point out that it's time entanglement, and what's happening in these other graphs is spatial entanglement. It's literally 2 vertexes and how those are entangled by an edge. It's a sort of different half of the entanglement, to the space and to this time. And I thought that was one of the most important things for them to get around, is that everyone's still stuck on this time-based entanglement, and they're not understanding that, oh, it could be time entangled or it could be entangled in space. Because that's the way that these photons work, is that they're entangled in time. Is that when you measure them from 2 different sides, of no matter how far apart they are, they're doing the same exact thing in time.
In time, that's exactly right. Now, the funny thing is, when we think about the distinction between space and time, and we might actually have in our heads maybe a Minkowski diagram, where we think like this funnel. So, these 2 cone funnels. So the above, which would be forward in time, and the below, which would be backwards in time. But to the left, rather to the left and to the right of those 2 light cones, we call them, in a Minkowski diagram. But on the left and the right of those 2 light cones, you've got these regions that relativity theory describes them, but they are disconnected from us in those 2 light cones. And that disconnection has certain properties to it, meaning that if quantum mechanics really is the underlying fabric describing even relativity theory, then quantum mechanics has to describe what's not only going on in the light-coned regions where we said that they're time-like, but also in the unlight-coned region where we call them space-like. And the point that Jeremy's really speaking to, and that I'm speaking to, is this idea that entanglement can happen in different ways. One entanglement is spatial entanglement, and another entanglement is temporal entanglement. And those light-coned regions of the Minkowski diagram functionally describe these different regions for which you can have these different types of entanglement. That's what I'm talking about. That's what we're talking about. And so Phoenix is able to capture each one of those different types of entanglements and demonstrate how they actually work and how they work together.
Yep.
So
interesting. We got a couple other comments here. Talk about examples of possible practical applications, please. Real world, not physical, not physics lab proofs. So practical applications. So, well, without giving away too many of our patent ideas, yeah, I'll let you do that then, because you're the one.
One of the ideas certainly is going right on back to the Alcubierre warp drive. So what we're able to demonstrate is that Phoenix describes that whole phenomenon. Where does the Alcubierre reside? Why can you actually do that in general relativity theory? And what's required in order to accomplish that? What we also are able to find is that this mechanism for creating warp fields also enables us to talk about what would otherwise be called chronometrics. We're able to talk about how time can also have this kind of an effect, how you can link different moments in time and get them to cycle between each other as well. But there's a lot of technological development. Another one that's pretty interesting to me is that we demonstrate how the particle itself is actually an algorithm, how it's actually a program. And the question about programs is what's the input and what's the output. So if you feed information into your algorithm, you're looking for it to spit something out, right? Some calculation that it's doing. So what we're able to show is how these particles are actually algorithms and what sort of best way of saying it, what sort of logical procedures is it actually running through? Okay, so what is a proton doing? What is a neutron doing? What is an electron doing? Et cetera, et cetera, et cetera. What are their interactions actually demonstrating, et cetera, et cetera. So we're able to decode the algorithm of particle physics and gravity. And what that enables us to do is then to begin to ask a much more fundamental question. How can we build a smaller computer? How can we build a smaller processor? Right. You know, because that's effectively what we're talking about.
Nuclear computers. It's the next step beyond quantum computers and what they're trying to do with these qubits right now. This is the next step.
That's exactly.
So we have that, and also if you can basically with our quantum disentanglement chambers, so to speak, we have this idea. Basically, you could create a chamber where you could use antimatter within that bubble or that chamber to break quantum entanglement to the inside, and therefore effectively negate gravity. So you could create a weightless environment on the inside. And that could be used in all kinds of applications, particularly pharmaceutical manufacturing, which they spend a lot of money to do things in space and to send things into space, to use microgravity to build a lot of molecules that can't be built in the ground because of microgravity. And so that would be a huge application right there that these people would probably pay a lot of money for.
Yeah, that would do that. Really huge. I mean,
microgravity experiments in the lab. Yeah.
That's microgravity experiments in any lab, right? You don't have to have sophisticated equipment in order to achieve this monumental result. And you don't have to, you know, fly your 1-ton payload at $1 million a pound into space in order to conduct that experiment. So it's a very, very quintessential manufacturing concept. So whether it's the pharmaceutical industry, whether it's the creation of better processors for your computer, in other words, idealistic computer chips, you can actually do that when you're reducing gravity. But we can turn that around. We can also create that gravitational effect in a microwave or in a slightly larger way, so that when you're actually in space, when you're doing your voyage from here to Mars, you're not having to build these gargantuan type of ships to accommodate you needing a spinning segment to allow people to be healthy in their voyage. We can actually demonstrate how do you create what would otherwise be called gravity plating.
Yeah.
So it's a very cool.
So I think that answers Corey Mailer's question about how far along towards laying out how to produce anti-gravity do you feel you've gotten with Phoenix so far. And again, we've gotten pretty far theoretically in being able to explain the Alcubierre warp drive, explain that whole break-off in space-time, how it occurs. So theoretically, we've nailed it. All we're trying to do is get an experiment based on setting this up where we artificially induce, you know, antimatter and get it to work to do this. So another thing, how do entanglements form was a question. And that, again, it depends on temporal or spatial entanglements. And again, I think a good example would be pair production and pair annihilation. You know, so a photon comes in, it hits a neutron, and it spontaneously, the photon splits apart into a electron-positron pair.
That's right, exactly.
Then that electron goes off, the positron will go off, find another electron, and the two will spin around each other in this sort of death dance, and then it will shoot out a photon. And we've gone through some of that in the math of how that happens. Where you've shown me with the, you know, this using the similarity equation and other matrix transformations and stuff to do these operations. So that kind of ties. I want to tie this into Jake's question here, and then we'll go back up to the question above that. But are these graphical representations of subatomic particles related, and if at all, to Feynman diagrams? And the answer is, oh, yes. Yes, indeed, they are. Go and find the Feynman diagram for a neutron, for example, or neutron decay. And then go and find on our particle list that we've shown you here the particles associated with that neutron decay. Okay, and they're on here. I'll point them out to you in case you haven't found them already. Let me get this so you can see. So here's the neutron right down here. It's this guy with this.
That's right, that 4-vertex.
So this vertex structure is your neutron, and then what you're going to combine that with is the photon, of course, which is this guy, and then there's going to be one of these involved. That's called the anti-neutrino.
That's right. And specifically the anti-electron neutrino.
Anti-electron neutrino, correct. And then I think there's going to be either W plus or W minus involved.
That's right. There's going to be and W plus, a W plus,
yes,
which is right
that one.
So
there's going to be one of those guys too, and
and a proton.
And a proton, yeah, because the proton comes out of it. So you're going to see basically graphically how do you turn, you know, this thing into that thing, and what do you get left over when you pull this stuff off of that, you know, to make that. That's basically the way of looking at it and doing it graphically.
Right. And if thinking about it is when you form that matrix of the neutron and the photon, the first thing look for are, you know, what's the characteristic equation. So if you know anything about matrix theory, characteristic equation is where you're headed on that. Another way is what are the eigenvalues of that matrix. But in the end, those are the simplest tools to use to see what that system of particles becomes. And what you find is that that system of particles actually can transform into a proton, a W minus, and an anti-electron neutrino. Let me just get that right. Oh, sorry, a proton, an anti-electron neutrino, and an electron. I'm sorry.
And an electron.
So, straight in your head. But yes, so that system of the 4 vertices for the neutron, the 2 vertices for the photon, can be transformed consistently into this outcome. And also can be transformed into simply the proton itself, the photon that you had starting with, and a W minus particle. So we find that the neutron's decay happens in 2 steps.
Yep.
The first step wants to form a proton and a W minus. The second step, and this is what generally takes longer, and this is why the neutron has a 10-minute half-life, somewhere around 10 minutes. But it's the idea that then those particles interact with this photonic structure. In so doing, get transformed further into the anti-electron neutrino and the electron.
Right.
So that's that process. We demonstrate exactly that same thing with exactly the radical.
Right. So it's to answer his second half of that question, his better question, he said, it would be how do they differ? And it's Feynman diagrams were essentially Feynman's way of saying, you know, like there's a state before, then some stuff happens. We don't quite know what it is. There's some stuff that happens, and then we have a state after. And these are what we measure in the laboratory for, you know, this was the state we measured before. Then I draw this diagram, a lot of hand waving involved essentially, and then what's on the other side. And what Phoenix has done is it said, no, these particles are really these things that can be represented in graphs, and graphically like this, and then you plug them into the Feynman diagram. There's no hand waving. You can actually see all the way that these loops and vertices are, and the information that's trapped on these vertices is literally realigning itself and moving off those vertices to these other states or arrangements. And
that's right.
There's no more hand waving. It's the step in between what's going on in the Feynman diagrams. That's essentially what this shows.
The main difference is that Feynman diagrams are what we call a perturbative approach to physics. We call it perturbation theory. It's the only way that you can use, that's what Feynman diagrams are. They are perturbation theory. Whereas what Phoenix is a non-perturbation theory. We're talking about the same physics, but 2 different approaches. So let me give you an example for the general audience of what we mean by perturbation versus non-perturbation. If I gave you the algebraic equation 1 over 1 minus z, 1 over 1 minus z. For you, that's a stupid algebraic equation. You put in a value for z, you automatically get a value out. However, we've learned in math that we can represent that very small equation with an infinite summation. So the 1 minus z can be represented with an infinite sum. It can be represented as z plus z squared plus z cubed plus z to the 4th plus z to the 5th plus z, all the way to z to the infinity. Right? So somehow mathematics enables us to talk about an infinite series of stuff which itself never ends. So every time you're using the infinite series, you're always asking yourself, okay, what's the next term that I can add on to make my understanding better? And that's why it's an infinite series. It doesn't have an end to it. Whereas it's actually equal to this very tight algebraic structure, 1 over 1 minus z. The 1 over 1 minus z can be computed with no real effort, no real problem. Any grade school child, if you just tell them how to do it, they can do it in their head, right?
Right. But if you take the Fourier series expansion of that function and then try to use that thing to calculate it. You get these close approximations with these infinitely complex and long and arduous calculations, which aren't necessary if you just knew what the heck you were doing in the first place. So yeah, it's there are some back end.
I was just going to say really quickly, Feynman diagrams are effectively the infinite series, whereas what Phoenix is giving you is the 1 over 1 minus c.
Well, Feynman diagrams, I would say the path integrals, because it's really, you know, the path integral approach, right? And that's essentially the math that's going on behind the Feynman diagrams. It's that saying that it's taking every single possible path through space-time until it finds the shortest and most direct one, and then it takes that one, which is absurd.
Right, but you account for all of them in order to find the one of them. That's exactly right.
And it's absurd. It's absurd to think that light's doing that, but it's what it's like. It just this amazing way of looking at it that it works, and the math works. That if you do it like that, it works. And
in fact, someone who's trying to approach this very same argument is Nima Arkani. I think that's his name. He's a theoretical physicist who has been working on something called amplitude hedrons. The amplitude.
Yeah, the amplitude. I posted a bunch of articles. That's the jewel at the heart of quantum physics article I posted from Quantum Magazine.
So basically, he's doing the same line that we have already resolved. But that's his pursuit. That's exactly what he's trying to do, is to come up with the 1 over 1 minus z, i.e. the non-perturbative approach, to this thing that we've been studying for decades, this perturbation-Feynman approach. You know, that be another way. He demonstrates without question, you know, that the other way has, this doesn't have problems, but it can be resolved in simpler ways. What we've been able to do is to get to the punch. So exactly what the simplicity is. And the reason that he hasn't gotten there, just to let you know, is because, again, for the most part, he's taking a top-down approach. He's not taking a bottom-up approach. He's sort of looking at math in the most general context and trying to ask whether or not, boom, you know, we can get this part out of it. And what we're resolving is that, no, we have the most fundamental part, and we're demonstrating, yes, you do get all of that out of it, period. And more, of course. But, so, yeah.
Right, and I just thought it's so interesting because I've always known that there was this idea behind it of like matter and mass being, you know, energy trapped, you know, on these, but I never really, you know, had a structure to how that was trapped before. And this makes perfect sense of things like why are quarks this 1/3 and 2/3 charge? Like, it's never made any sense. And like, you know, how can that have a third or a negative 1/3 or negative 2/3 charge? Like, how can it have a, you know, what's charge?
What is? And for us, it's loops and iterates. That's what's defined from the charge. And on top of it, the real issue that always punched me way back when about quarks, and this is why, although I didn't mention his names, there were two people that originally influenced me. One was Jeffrey Chu, and the other one was Friedrich Capra, who wrote the Tao of Physics. So I was in high school, you know, just loving his works. But what he and Chu are talking about is something called bootstrap theory, which effectively tries to argue that quarks aren't actually real, that they are patterns in something called the S matrix, but that's all they are. And what we're able to demonstrate is exactly that point, that these things are really just patterns. And those patterns are these, you know, 2 loops, 1 loop, etc. But those patterns have this peculiar property to them, that they always must be connected to other patterns. There's a consistency of how these patterns can exist. And those quark diagrams, the 2 loops, cannot exist on its own. The 1 loop with 2 things just splitting, they cannot exist on their own. They are bound in these graph structures. That's the critical difference, and that's exactly what quark theory is saying.
So about the gluons too, because there's this whole idea of this thing called a gluon that holds these quarks together inside the nuclear model of modern physics. And with this, it's like that edge is essentially, does that replace the gluon? Is there another understanding?
Functioning at the gluonic state that's binding these two vertices together. The beauty is that this particular way of looking at it actually has, you know, what we call a scattering theory representation, where we can further draw out the next part of the question is, well, what's the potential? What's the potential energy structure that's defining this gluonic behavior? And so we can map that out completely, and then demonstrate that our gluonic structure is exactly the Yukawa potential. It is exactly this we expect to see with strong nuclear behavior.
Now, what about proton-neutron coupling? That's, I know I keep asking you about this, and you tell me the same thing. So,
what I tell Jeremy is that we got to get down the simpler things to understand before we get to these more advanced concepts. But yes, Phoenix actually has and holds within it the entire description of the atomic nuclei. So we don't just know, why particles are stable, but we also know all of the end results, meaning how many neutrons can I add on to an original structure before they just won't stick.
Yeah, exactly. Because essentially, if you can get that right, then because you got the basic building blocks of physics right, but in order to build chemistry, the next step up, you need that, and that's going to be so that will be a huge step to show that, and I can't wait for more to come out on the theory, and as these new papers get published, especially the scattering theory and quantum field theory, and how to derive our friend the Schrodinger equation from combinatorics and combinatoric principles. Again, combinatorics is it's the ways of counting. It's just math that looks at ways of counting things, and
that's why we can say with certainty from the theoretical standpoint that a measurement is nothing more than counting structure, because in fact that's what combinatorics is saying. That's exactly the statement of combinatorics. So all of our measurement, all of what we do in science is governed by that very simple principle. I mean, it seems stupid almost, but no one ever really says it, except unless you're talking to a combinatorist. No one really ever says that, right? Which is all you're doing is counting structure. So the next question to ask is, well, what's the most fundamental structures to use? What's the core alphabet, right? Yeah. So Phoenix defined the alphabet. So by that alphabet, we can write words. From those words, we can construct sentences. From those sentences, we can construct paragraphs. From those paragraphs, we can construct, chapters, books, libraries, et cetera. We get the whole thing. Okay.
I think it's an important step, though, for people to take outside of this. This is a bag of vertices that sits at this point that is this particle, but then there's space between all the particles, and there's a lot of space between even the core, even these things in the proton's nucleus and the outer shell where the electron sits, some real far distance away from that, and there's reasons for that and how that works. And I think that's sort of what I'd like to know is what is space beyond that, and how do we get space, and it's sort of with this entangled model where you explain that we think about the Big Bang and what the state of the universe essentially looked like before the Big Bang, and you could say that it was essentially one vertex that was infinitely entangled with itself, or an infinite number of vertices which were infinitely entangled at one point altogether.
That's right.
And that something happened.
So the idea, So where Phoenix stands in this is the idea of a state space. What do I mean? If you're dealing with people in quantum mechanics, they'll tell you, firstly, that there's something called a Hilbert space. And the Hilbert space is just a question of, well, how many things can my particle system become? Possibilities, right? That's what we call the Hilbert space. And so it maps out all of the different things that, you know, your quantum system can ever evolve into. Okay. Well, for us, that state space is space, meaning that each one of the states that you can engender, design, pony up, each one of those states has a whole variety of things that it can become. And each one of those states is in fact functioning as what you and I would call a single point of space. And how you get from one point of space to the next point of space is how you evolved in time. Okay? So the whole idea that the Hilbert space is a state space where you look at how things evolve through it and blah, 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 blah. For Phoenix, that space is space. That's really what's going on outside of you. Another way of seeing it is that it's a movie film. And one of the excuse me.
You got hiccups, man? Yeah. Why don't you get a drink of water?
But short of my hiccup, basically showing how excited I get. One of those states is one film, one frame in your film. And then all of those frames are linked up together to form a movie. The movie is reality that you see before you right now. Okay? It's no different than saying, hey, I'm looking at my television screen, or I'm looking at right now my monitor on my phone, and it's really just a vat of pixels. But somehow magically, I'm able to see motion, I'm able to see 3 dimensions, I'm able to think I'm participating in this matrix called my television screen, but that's what we're talking about. The whole world around you is really functionally in Phoenix this state space, where each one of those states, each one of those points of space in front of you and all around you are really just one different manifestations of any point, any one of those points. So it's almost like that, it's not almost, it is that Hall of Mirrors effect. Okay, so if you walk into a Hall of Mirrors and there are only 2 mirrors, you're probably going to go, hey, this is a Hall of Mirrors. But if you walk into a Hall of Mirrors and there are a quadrillion tiny mirrors in there, trust me, it will take a long time before you figure out that things that are going on in front of you are actually not simple reflections of you. So it will take you a very long time to figure that out. And so what we're saying in Phoenix is that model says that's really what's going on. That there are these different states which are all representations of each other, different possible ways in which something can evolve, a singular point can evolve. But once that evolves, you have these things that we call the space around you, and they are all connected in these moments of time, meaning that it takes time for you to look at your finger. So I look at it at my finger, time has to elapse before that happens. But that's what we're describing here. We're saying that everything that happens in front of you, every point away from you in space, has this evolution in time. It's what we call a state space. And for us, the state space is space. So, in a nutshell, that's what we're saying.
So yeah, I think looks like we've covered quite a bit. I was hoping, maybe go later if we got more people and got more, questions and stuff. So one of the questions we got another one. How does Phoenix relate to work with holographic theory? That's a good one. That's a really good one. And simulation theory. That was another question I meant to get back to, but we keep getting distracted. So can you please explain how is simulation theory related to this? So holographic theory, simulation theory, it's the idea that we're living in this, that the world's a holographic and that we're inside of a simulator, or that, we could be on a computer. And, this is an interesting one because I don't think that we are on a computer, because it would certainly, there'd be limits to the function and limits to the things within the program that would let you know about that. But could you create a program? That's more of our question is what Wolfram's been trying to do, or what he said he wanted to do in that article on what is space-time, is the idea of computationally coming up with physics through a computational model where you could basically run our universe in a simulation. Could that be done?
Yeah. Yes. Easily, actually.
Right.
That's the beauty of it.
Do we live in the Matrix? And well, yes, according to Phoenix, according to this theory of physics, everything's a matrix. Yes, all these particles have matrices which represent them. Like, we could literally describe everything we do as a matrix. That it all works in this sort of matrix, and that literally Phoenix, what we've showed, opened the doors to is the programming, the set of rules or algorithms that you would have to program in your computer algorithm to create a universe very much like our own and very similar to our own. So, the dark matter and dark energy, of course. Yes, as we mentioned before, if you start connecting more and more vertices and create a bigger and more complex graphs, and then find the matrices for these, and then see how those, put them inside of a formula with some of these other particles, regular particles like neutrinos or electrons or protons or neutrons, and you'll see that these higher order particles are inert. They do not react. They're exactly what we think dark matter is, and they explain dark matter. In fact, that dark matter and dark energy are a result of these higher order particles, these higher order trapped energy states, essentially, that don't interact with normal matter. And we can show that they don't interact with normal matter with the same matrix mechanics that we've showed to show that this stuff reacts and looks like regular matter. So,
in addition, what we're able to demonstrate is why is it that gravity is really there for all of these particular configurations. So they all have a measurable gravitational effect. What they don't have is necessarily an interactive effect, meaning that if you try to force an electron to interact with one of these dark matter particles, it just doesn't give a crap about it being there. It goes right on through. However, they do influence each other on a gravitational basis. And that's the other reason why quantum gravity via Phoenix works so beautifully, is because it demonstrates exactly that fundamental concept that general relativity theory says, which is we don't care what the matter is. If there's matter, it's gravitating. And we demonstrate the same thing. So it's a very...
Well, we haven't done that yet, but that will be, I think, in the third paper.
Yes, that'll be in the third paper. That's exactly right.
So, Tom Reef asked if quantum entanglement is a broad term for what we're talking about, and I think he might have missed what we were saying earlier and what we talked about earlier, which was that there's two different types of quantum entanglement. There's the term that they're thinking about, most people are thinking about when they hear quantum entanglement, is the temporal entanglement. It's these two photons which are entangled in time, and that's why you look at one and you look at the other, and one's up, the other one's down automatically. They're basically the same photon, but at different places in time. It's the same photon that's entangled in time to itself or to each other. And these are what we're talking about is photons, which is light energy. Energy equals mass times the square of the speed of light, and that says that matter or mass is just energy that's traveling at the speed of light. And Phoenix theory shows how that energy becomes entangled or trapped on vertices, and according to these special rules which create particles. And that's what particles are, is that they are in fact energy that is trapped on vertices, and it can only be trapped in certain ways, and the ways that it can be trapped form these series of particles that work this way. Remarkably, and no one in graph theory ever discovered this before, messing around with these very simple graphs. No one ever figured this out.
Even some of the most quintessential combinatorics, and I followed their work, two guys, Philoget and Sedgwick. One was the head of the computer science department at Princeton, and also helped to create the Adobe systems. And the other one was a Frenchman who I don't know, outside of math, what his other interests were, but these two brilliant combinatorics came together and really unified combinatorics. They call it analytic combinatorics. But the point is that even with everything that they're able to do and have done, they've written volumes, it's not in there. Okay, and I was the right person at the right time. There's just no way around it. Chances are there's somebody else too.
I guarantee you there's other people that have figured this out or were working on it but haven't published it yet. And it could even be that, I've mulled with the idea that someone's figured this out a long time ago and has been purposely pushing university in the wrong direction for a number of years to sort of muddle this up, because someone's got to have already figured this out and might be using it. Yeah, exactly. Do you think this stuff might already be figured out and being used? It's very possible, because it's really, as you'll see, any graduate student who's taken linear algebra, maybe graph, you don't even need graph theory, or linear algebra, a little bit of matrix theory, and some math, physics, and a little bit of knowledge of particles and quarks, and you're well on your way to being able to understand and chunk this math and work through it. So it's
that much more difficult.
It's not that. It's not much more difficult. It's not more difficult than the conventional approach to quantum physics, which is the Schrodinger equation and path integrals and perturbation theory. So. Question here was, have you had any big university researchers react to your work yet? And the answer is no, not any big universities. We've had some PhDs who are professors at other universities. One guy was a chemist, contact us. A couple other people who are PhDs in other university or college professors who are interested, who have gotten the video and want to know more or want to learn about investment opportunities because they're interested in investing. And again, we're working on getting the investment platform fully set up. That should be set up sometime around mid-January, towards the end of January. And all the donations that we're receiving at this point now will be transferred to that stock options once that gets set up. So does this data play well? Oh, sorry, go ahead.
Let me make this really quick point. In 1905, when Einstein published, his papers, his miracle year papers, the only physicist he had working with him was his wife. Okay, basically the physics community had veritably given up on him, right? They certainly gave up on his wife, who was the first female physicist at the same school. But the point is that he had to work in the patent office just to survive, right? So all of the ideas that he came up with, he and his wife created this thing out of the blue. The physics world had not seen anything like it, and so the point of, how many other professors or how many other institutions or how many other professionals, you might say, are involved in this it seems like the appropriate question to ask, but when you really dig down into it, the revolutions that have happened in science and physics have almost never come in those ways. They've always come from those Einstein-like people. I'm not considering myself an Einstein. I'm just saying that they always come from those Einstein-like people who just come out of the blue. And
right, and I think it's interesting is that in order to get published and to get this theory out the mainstream ways that people are posting about, like, oh, why aren't you publishing in mainstream journals and getting your work published and doing this? And we are publishing it. We're putting it out on the internet for everyone to see. And this we live in a time period now where we have that unique opportunity where I can literally put something out on the internet and it gets out to people. I don't have to publish it in one of these mainstream journals. In fact, those mainstream journals, you would have to publish a bunch of other boring, unrelated articles and establish basically an authorship for yourself in those journals before you could even publish anything close to being, revolutionary or groundbreaking. And the really groundbreaking and revolutionary stuff, they wouldn't allow it to be published in their journals anyway, because A, it would be too controversial. You're overturning too much of established mainstream dogma.
That's right.
And two, it's not beneficial for them because they're gonna Yeah, there's just so many different ways you can go through the list, but you can't publish this kind of a thing. It's the equivalent of Galileo, you know, telling the Pope to look through his telescope. You know,
right. He didn't see any mountains on the moon. There were mountains. He saw them. He just wouldn't recognize them. But let me give 2 examples. One example is Richard Feynman, who was giving really the first lecture on his solution to quantum field theory, and Niels Bohr, aging Niels Bohr, was sitting in that audience. So when Niels Bohr saw what that man was putting on the blackboard, he stood up and walked out. Now, Niels Bohr represents quantum mechanics. That's who quantum mechanics was. He was the guy who said yes and no, and he veritably said no.
Yeah, he veritably like laughed in the face of it, like this is like, it can't be like this. It can't be like this. It's a stupid way of looking at all this work, and that's the accepted way that all the physicists at CERN now do particle physics and do these interactions, is with Feynman diagrams. What the father of quantum field theory at the time considered ridiculous. So yes, revolutions in science don't. We've thought about this. We've done our research, and we believe that we've gone about it the right way. That's all there is to it. So again, people have said, "Oh, what's going to happen with this patents? The patent office is going to steal it. They're going to kill you and confiscate the patents, like they've done to so many others." And honestly, I've done the research into a lot of those cases, and yes, that happens in certain cases. I've seen the way the patent office uses censorship, and it's certainly a real thing. But there's a lot of people that use that as just basically. They create this further they never had anything to begin with, so they create this further conspiracy to say, oh, you know, and then the government took it away and they covered it all up, and then they, you know, killed everyone involved, and that's, you know, but you know, really it's really, did they have anything to begin with? They have anything that was real? And like Stanley Meyer's water car that he supposedly created back in the 70s, it's 2020 damn near, and we still don't have water cars. Like, somebody else didn't figure this out. Like, I don't know. It's some things are real and some things are not, and that's just what you have to learn as you sort your way through this stuff. So really experiment again. Yes, experiment's the way that we're going to determine if these things are real. And I want to talk to labs out there that want me to come and look at their experiments or something too. We're also willing to do that, to work with other labs that want a secondary opinion or verification of things. They can certainly hire us to do that for them. But we're going to be, you know, focusing on the facts, not anything else. So talk neurolinguistics and photonics. Does this data play well with the data from CERN? Yes, all of the main particle interactions are in all the particles that they're finding at CERN are well within our map and can be mapped out in Phoenix and using Phoenix. In fact, Phoenix even creates or predicts some particles that they haven't looked for and that might be hiding in the data at CERN, which, again, the data that they get at CERN, they get quite a bit of it, and they can only crunch so much, so they only look for certain things in certain areas that they only have time to do, and so much to look at so much. So there could be evidence for Phoenix or other particles predicted by Phoenix hiding in the CERN data right now. They would just haven't looked in the right place. Yes, that's true. Well, big oil companies have crushed a lot of things, and you know, they have been involved in conspiracies too, or known documented conspiracies, like this streetcar conspiracy where they went and bought out all the trolleys, and so that people would have to buy cars to get around. They wouldn't have trains anymore and public transportation. That happened. So yeah, there's suppression of research and reach. You know, like, it's odd. Yeah, my channel has 75,000 subscribers, and yet we just reached that maybe a day ago, and it doesn't get out to all those people. And I think that, I'm not sure how that works. I think that there's a lot of people on my subscriber list that either have inactive accounts that went dead a long time ago. They now have new accounts, and that these accounts are still subscribed, but they're sitting there somewhere in dead space, you know, so they don't get the message. I don't know, because there are things that have made me think that my viewership has been held back and suppressed with the reach of a lot of the videos and YouTube stuff that I was putting out. I do think it's interesting to see how this video is taking off and the view count is going up. And I don't know what's going to happen with it, but it's definitely an interesting phenomenon. And so is there any chance that your theory could fail? There's always a chance that any theory could fail. How confident are we in our theory? Seeing that it describes all of known particle physics and every known interaction that you could possibly think of in every known particle, and we can get combinatoric relativity theory out of it, which relativity gives you magnetism, it gives you electromagnetism. We get the electric field from this with charge, and that's all described. Yeah, I would say that we're pretty confident in the theory. I mean, I've seen enough from what Ken has shown me, and he's shown me a lot more than we've shown everyone else too. So I'm pretty confident in this as a theory, and I look forward to experiments to give us that further confidence, and also simulation. You know, there might be some computer science groups out there that are interested in this sort of thing and might want to talk to us as well to get some input data for their computational algorithms and testing of that end of it, because there's going to be some of that involved as well, as any good scientist or mathematician or modeler knows. They model things in computers. So, what else do we have? Why keep it secret when one can make billions from releasing the information? Well, we've kept certain things secret. Okay, we've given enough about the theory. We've dumped enough on you and shown you enough of how to do it and what it entails, and described enough of it about you that I'm sure that there are people out there that are already the people who are really good at matrices and doing this kind of math have already started pouring through it and really getting into the math. And I guarantee you most of those people are probably in China and Russia, unfortunately. Well, the Americans think they know everything and are dismissing it with a bunch of hand waving and calling it a hoax or bullshit. Our friends overseas are probably hard at work going through the math on this. So it's hard to say, you know, release what's too much to release and what's, you know, enough. And I feel like we've released more than enough. Actually, I would feel a little bit dangerous about what we have released, because in the hands of the right person, they could take it and build exactly what we're talking about. And warp drive technology, essentially, with the antimatter and antimatter states, if they figure it all out and get it all, you know, and really have this down and understand it conceptually and get a bunch of good physicists on it, they could beat us to the punch. We're hoping that doesn't happen, that we have enough of an insight and enough insights that we've left out that we can successfully do it ourselves and be the first. And we're hoping that we can do this by 2020. I'm hoping that 2020 is sort of this, I have this prediction for 2020 is this vision year. It's this year where things are going to be coming into focus for a lot of people and a lot of things. It took me 2 years of going through this, since it was about 2 years ago that Ken first introduced me to this and showed it to me. And it took me about 2 years of going through it until I really realized what he had. And I think it's going to take other people a similar period of time before they realize, you know, just what the heck they're looking at and just what the heck these guys are talking about and what they have. So it's going to be a process, and I'm fully expecting the next 2 years to be a lot of hard work and a lot of uphill battle trying to get things put together. But at the same time, with what we've received so far and just response since we put out the video, the amount of emails that the quantity of people who are super interested and have the money to throw towards this, I'm really confident that we get this investment platform set up, show people that we have a solid place for investing, and that there is going to be a return, that people will be getting something back, that we actually have, you know, what we have in mind, and a little bit more about the experiments. Of course, we're still talking to other laboratories out there and trying to form partnerships with these other labs to find the right arrangement and setup. So we're talking to a couple people right now. We're going to be meeting next week to go over that lab, to look at one particular lab. And we're going to be looking at other options and talking to other people as the emails and other contacts start flowing in. We're really looking to get hooked up with a lot of the right people, a lot of like-minded people in this process. I'm getting a lot of emails from a lot of different people on different interest levels. So it's certainly things are moving forward and falling into place, and we're getting the right type of people and the right group together to get this thing off the ground. And I think that the investors won't be a problem once we show people the platform, once we show people a little bit more about the experiment that we're going to perform. And then once we perform this experiment and hopefully have successful results, that proof of concept, that hopefully be the Kitty Hawk moment that we're talking about with this HoverBrothers, Wright Brothers sort of allegory. Yeah, so hopefully that we can produce that, you know, aha, this is it, you know, here it is for you. Now you have something to see. Now we can move forward and scale that up and figure out what else we can do with that to again, the patents on usable technology, things that we can sell to industry, just a way to fund a larger mechanism to do more research and to do more detailed experiments and larger scale experiments, and eventually the ultimate goal of starting this aerospace company and actually building craft, like, which has been a dream of mine since I don't even know how long. And we've done all kinds of working with all kinds of people doing experiments with those lifters and the electrogravitics and all that other real primitive workshop stuff. It's a 100-year-old technology now. I think it's a joke to even, you know, entertain it as a real propulsion system idea at this point. Warp drive physics is the future. It's the holy grail. It is the ultimate propulsion technology out there. It allows faster than light travel, which warp essentially, and it's how you get from interstellar. You know, like a lot of people have rejected the idea of alien visitation altogether because they speed of light, and they reject the idea of being able to travel and traverse those vast stretches of the cosmos to get here. But with warp drive technology and wormholes,
right? That's right. You got it.
Your problem's solved. So.
I mean, you know, it's funny because if you really try to really think about, well, look, there's a gray alien, and that gray alien might be mortal, but the idea is that normally what we find on biological systems is that when they reach certain sizes, they have a tendency to have the same clock, right? For us, the clock is 80 years at most, somewhere around there. Biological systems, and we would just make the assumption that that probably happens on other worlds of biological systems where they'll reach a certain stage and size and certain clocks. In other words, it's reasonable to assume that a gray alien, not, you know, made up out of computer chips, you know, is reasonably, you know, short-lived like we are. Because that's the tendency of biological systems, to have a kind of mechanism. Yeah, maybe that's not true.
Say not a gray alien, just say an EBE, an extraterrestrial biological entity.
An EBE, exactly. So the EBE is actually talking and walking around with us, then there's a chance that they're probably on our scale somewhere along the way, whether it's size-wise, whether it's timeline-wise, meaning that they don't function for over 80 years continuously.
et cetera, et cetera, et cetera. I mean, there's some broad assumptions one can make. It's no different than you, bacteria, right? So the bacteria don't live very long. But then again, we don't really communicate with bacteria. We look at them from the top down, and we're like, okay, whatever. But the idea is that these EDEs are interacting with us, if that's really what's going on, and so that we can make a reasonable assumption about them. And one of those reasonable assumptions is that they're not 10,000 years old. Okay, that's a reasonable assumption. So in that reasonable assumption, we can also say, well, chances are days pass in the same kind of way for them mentally as they pass for us. What do I mean? I mean that if they're in a flying saucer for 20,000 years, they're going to get freaking bored. Okay? They're not going to be living a happy life. Now, I don't know, maybe they go to sleep for 20,000 years. But there are some broad assumptions that one might be able to hand wave through that give rise to the idea that that EDEs are getting here a lot faster than we would like to believe, right? So that maybe their transit is a month and not 10,000 years. Yes, I know that they're going considerably to the speed of light, and
yeah, so 10,000 years it's going to take them traveling at at regular speeds across these vast distances of space. So they're going to, yeah. No, I get your point. Assuming they have the same timeline as us, they're not going to, live and die in these space capsules. Like it's like that idea of that NASA put forward that they're going to send this massive ship to Alpha Centauri or one of these nearby stars, and it's going to be like the entire crew is going to die and like reproduce on board 5 times, but like it'll be the 5th generation of kids that will be actually arriving there, and their grandparents' grandparents and grandparents will have been born and lived their entire lives on that spaceship as it was in so actually I found more questions on here. I didn't realize my thing wasn't scrolling down, and I was missing a whole bunch of questions, so a bunch of them to catch up on and stuff. So
sorry guys.
One of them was okay, so one guy wants to simulate Phoenix theory in Unity. I think that would be really cool. We need more computer programmers looking at this stuff and starting to come up with simulations. What are you hoping to use to interact with these particles to manipulate them? Well, some of that's proprietary, and some of the particles we're going to be using are also proprietary too. And so we don't want to get into that too much because we have some idea about how to go about that. But it's where can I go online to research this topic? The theory page has a bunch of resources already on HoverBrothers.com. If you click on the theory page, and you can check out the stuff there. And Ken's got a whole bunch of these videos where he sort of goes through the matrices and the graphs and explains what they mean and goes through it all. So you can go through all those, and then you have questions beyond that, we'd be happy to answer if you send us an email. Do you have any idea how much energy would be required to make something like this work?
No. The reason why not a lot is because we understand on particle level what we're dealing with. When you're talking about the Alcubierre warp drive, or the white version of the Alcubierre warp drive, what they're missing out in that perspective is quantum mechanics. Okay, and that's why
they're all GR guys.
They're all GR guys. That's exactly right. I mean, I'm not trying to downgrade them, but their perspective is missing this very fundamental thing that Alcubierre couldn't resolve. Where is the negative energy? Where is that coming from? How do we even manipulate it? Well, when you begin to ask those types of questions, you're really now wanting to talk to the quantum people, to the particle physicists, to see if such stuff even lives in the universe.
Right.
And so we understand how to manipulate it. We understand how to use it effectively and efficiently. We understand how nature uses it. So yes.
So yeah, what else do we got? What you have released is perfect. Thank you. John Castillo for that. Perhaps others, instead of stealing these ideas, will be interested in invest in experiments with you guys to get this off the ground. That would be awesome. I couldn't have left a better comment myself. In fact, are you sure you're not reading my mind? Out of my imagination, out of my imagination, I wonder if Phoenix model can control atoms to bind at a specific location to create the holodeck tech as seen in Star Trek. All right, well,
yes.
I mean, holodeck, yeah, it displays
what we're talking about there, sorry, what we're talking about there, at least in my opinion, is information.
Yes.
So what Phoenix to demonstrate is what information actually is with respect to particles. You know, what is this? You know, we kind of see it. We certainly use it with our particles, but we don't understand that the particles themselves are little bundles and joy of information. Mm-hmm. So what we're able to do is to demonstrate that part of it. And if you're, you know, capable enough of taking it from that level, you can certainly take it into a holodeck scenario.
That's interesting, because holodecks is a lot of the background that I come from is in control systems engineering. That's what my dad does, and what I sort of was doing for a while was with this system called Crestron, which you can look up, and it's a kind of like a control system, and it has touch screens. It's touch panel automated control systems, and it's very much like what the holodecks are in Star Trek. It's literally you just making these buttons and putting them up on a screen with a HUD or a heads-up display, and making it so that you can push on these things, and they carry out functions or programs. So yes, that's definitely all in the works, and when we create our spaceship, it's definitely going to have a holodeck in it with a very intricate control system that I will be helping to put together. So when you identify the particles, how will you be able to manipulate them? Well, you put them in the matrix with another particle, find the eigenvalues, and see what you get, and you go from there. Try putting different particles in with that particle, and chunking it through them with the matrices and seeing what you get, seeing what these things produce. What do they?
And produce with what probability, right? So you can tailor the probability to what it needed to be. Do you need it to be 90%? Well, you can see all of the possible particle reactions, so you really know what to put in to get this effect. So yeah, I mean, this is really the score of quantum mechanics. But yes, that's how we do it.
Yep, and I'm going to keep going down the line. Carlos Ray Kurzweil said one of the seasons of aliens haven't visited us is maybe one of the reasons that aliens haven't visited us, maybe because we are the ones that are ahead tech-wise. Okay, well, yeah, obviously if we're ahead of them, then they wouldn't be able to visit us because we can't visit them. So, but yeah, you'd assume that. But again, the universe has existed for billions of years according to our models. So in that amount of time, it's not feasible. Even a million years of human evolution, if we were to survive that long and not kill ourselves off, would be our technology would advance quite sufficiently. I would imagine, and this is literally that next step that we're trying to take before humanity kills itself off. Our last little try, one last stand. Why do you think possibly an EV would fear the nuclear bomb? Do you think with all this information connected through entanglement, splitting atoms have effects on a larger scale? Well, there's not really related to that, but the idea that kind of the idea that from first contact in Star Trek, was that when we first warp flight in First Contact, it sent out this a luminescent sonic boom out in the galaxy, and that's what the Vulcans picked up on and came and made First Contact, because they're like, oh, a civilization that just jumped to light warp technology. You just developed it. Now, welcome. that was like that defining moment that happened, and that one of the probably the best Star Trek movie ever produced. Was that First Contact, but there's other people that afforded that same idea that when we detonated the first nuclear weapon at Trinity, that we sent off this massive radiation like a signal. It's basically like a beacon, a lighthouse that just beacon that just appeared in the galaxy, in the cosmos, that said, hey, we've reached the atomic age. You know, here's a frequency of this, you know, here's a light of this frequency being sent out. And if we assume that our detectors are going to be looking for things like that too in the future, our SETI satellites and stuff like that, so that we can detect when other civilizations out there might have reached that same point in their technological evolution. So again, these are interesting points that, you know, like we're doing these things like atomic tests or the tests, the warped kind of tests. There might be other unforeseen consequences about what kind of signals that we're sending out into the cosmos that other life might pick up on or see. So it's certainly it's a consideration.
It is. Absolutely.
There has been talk that a type of Alexanderson antenna can produce a Stargate. Portals and Stargate technology is very similar to wormholes. If you open a wormhole at 2 different points and literally connect those 2 points physically in space, you could essentially create something similar to a portal or a wormhole or a Stargate.
That's right. That's right.
It's not too crazy. A lot of things that's great. What is crazy is that science fiction is quickly becoming reality. You see that all around us with a lot of these other technologies, and this is really the next one. Yeah, so this guy knows what Crestron is. Awesome. Yes, an awesome control system. It is literally the Rolls-Royce of control systems. Yes. What better control system you need? It's compatible against all. It's integratable and compatible with all kinds of other different systems and control systems. And it's a great setup, great software. It's very complex, and there's all these little intricate little bugs to it that you have to work out and know, because it's one of those things. But yeah, again, Crestron, great. Glad my people are on that level with me. They know about that. So here we go. Sweet, thanks, Crestron. Can we invest by buying shares instead of just donating cash? Yes, eventually, if we own shares, that could potentially grow, and then there's an incentive to invest a lot more money. I agree, and we're encouraging people to invest, $100 or so for now, just if they want to donate something through the donate button of the PayPal. Just donate like $100 just to get everything going. We've got enough, quite a bit of donations coming in already, and we're using that money to basically set up and pay off all the legal fees and other things that we have to do to get that investment platform set up and get that information filed and get that thing going. So yes, we're working on that, and again, we agree and understand that more money and bigger investments will flow in once that infrastructure is there.
Yes.
Star Trek: The Motion Picture was by far the best. Okay, there's no proof. There's no like definitive proof. It's not like a mathematical statement we're saying here. It's really it's a taste thing. It's like chocolate cake's better than pineapple cheesecake or.
I do as one of our experiments into the futures is to be able to send a probe to reach up to Voyager, take a photograph, send the image back faster than the speed of light. So, I mean, there's a lot of things that, we've thought about that we will play with just to demonstrate that this stuff really works. There is one of those catches. Pioneer, Voyager 2, etc.
Let's see. Here we go. What do you think of the EM drive? That's NASA's M drive, that resonant cavity thruster. I think it's real interesting, and we're going to, of course, I want to look at all different types of propulsion, and and go through a list and be like, I want to essentially be a backup lab to do other testing and verification of other propulsion technologies and other things. And EM drive is cool, but as far as propulsion devices go, you can't get better than warp drive. Warp drive is the is where it's at. If you talk to anyone in propulsion or knows propulsion, and again, there's the STAFE 2 conference is one of those conferences, the Space Applications International Foundation. You can look that up. That's a conference that basically where people go to talk about new propulsion ideas and technologies. That's where those M drive guys presented their stuff, you know, probably presented it to get a lot of their funding to do what they did and create what they did. So yeah, again, there are these advances that are occurring and happening. They're pushing technology in the right direction, and it's going to start from people like us doing it, stepping out and thinking outside the box. So I got some other comments here. Not of them all are really questions. It's just, you know, more comments. People saying that I think we are the petri dish. Aliens have been manipulating us for a long time. This did not just occur because we split the atom. Yeah. Again, it's interesting to think about, and interesting ideas as well. So, you know, regardless, the petri dish is about to figure out how to. The bacteria in the dish is about to figure out how to escape the dish. So watch out. So.
Lab broken free from NIH. We're on the loose.
Oh yes.
You're not going to put us back in that laboratory. No cages, no petri dish.
No thanks. So the guy in Cal Fullerton doing piezo inertial propulsion work says his theory applies to wormholes as well. I haven't checked out what he's doing. I'll have to look into that. That sounds interesting. Tim Pickerel, I'll make a note of that. Does this theory have any applications for medical science? As we pointed out before, yes, medical technology, especially pharmaceutical manufacturing, relies a lot on microgravity environments for a lot of the chemical and production processes. And if we were able to use this quantum entanglement theory and to shut off gravity via shutting off quantum entanglement, we could essentially make chambers, microgravity chambers for conducting these tests in any laboratory here on Earth. You wouldn't require space laboratories or laboratories in planes that would have to do these, you know, to create these moments of zero gravity environments, microgravity environments. There's ways to do it that are very expensive, and you know, this would be a much more applicable way we could directly sell to industry, and it would have direct applications for medical science. And not to mention what other kinds of things could be done with medical science if we understand what's going on in the information level of physics. Again, one of the things from Star Trek with medical science wise is this idea of the tricorder. Essentially a thing you could point at someone and be able to diagnose or tell everything wrong with that person. And it's definitely an idea I've thought about. And you could maybe, yeah, there might be some applications for that. It's, again, very advanced systems. Medical human bodies are very advanced macro scale systems. This is really, there might be some applications there further beyond what I've seen and foreseen. But yes, certainly medical science. If humans are genetically engineered from advanced ancient aliens, then it's just a matter of time before we make that huge leap forward. And unfortunately, money is an obstacle that we still need to move forward. Right, and yeah, nothing. You're right. It can't be done for free, and so hopefully the investment platform, and there's enough people with money out there that can get this together, at least to the point we need to produce that very first experiment and get that aha moment for the world to sort of say, like, look, now you can invest, now it's safe, because, you know, we've gotten that, you know, question out of your minds. which I agree. You know, people should be skeptical of this. They should be like, these guys, you know, I wouldn't believe it too if I seen someone else put out this. So I'll definitely go and look into it. Did you make T-shirts showing a graphic of the 10 Phoenix particles? Oh, it would be more comfortable wearing that instead of the flying saucer T-shirts. Phoenix should be promoted more. I agree. Yes, particle physics and more like physics-based T-shirts that are less alien and UFOs.
Okay.
That's a good point. I'm like wondering why we just did all these great graphics and I put out this whole store with all these shirts. And I'm like, how come no one's buying these things? They're looking into them or buying them. Like, what's going on? And I think you might have just tipped me off, Marcus. Thank you for that. So
we do have a particle on that on the UFO.
There is a particle on the UFO. Yes, we have the W plus particle on the UFO. But yeah, I think more scientific based shirts with the real particles and then some matrices and stuff. I think that would, I mean, as far as the physicists, you know, the people out there in the physics community that like are physics students, showing up to their class with a shirt with these particles on it, yeah, that's going to be a lot better than showing up with a UFO or a flying saucer or an alien head on your shirt. Yeah, I agree. So yeah, I'm right with you right there, Marcus. We're going to have to come out with some more T-shirt designs and we have the graphics, so I'll just have to go and put those together with some designs. That's
we got a lot of designs for you. Thank you.
That's a very good point. We need to promote Phoenix more and do Phoenix T-shirts. Yes, I agree. Interferometer came out of the NASA work as well. Yep. I'm not sure what you're going with that one. What kind of time frame wise from discovery to warp drive? Sorry, distracted at work.
The idea is that what we're attempting to do is to demonstrate experimentally that we can distort space-time. Now, the theory is already in place for what warp drive is. So we already fundamentally, on a theoretical basis, know what warp drive is, how to do it, how to get it to work. But the step to it is just to demonstrate, firstly, that this actually is a measurable effect, that the theory is right. And then we can really bust some guts and go much farther, much more quickly with it. So.
Yes, so one guy pointed out, yeah, I don't want to bash your beliefs, but you don't look very serious with your alien saucers. It's just unprofessional or something. Or he didn't say unprofessional, but I'm sure that's what he was hinting at. I don't really see the link between physics and aliens. I know, I'm sorry. The aliens thing right there, I want to believe that's my sort of persona. I'm like, I've sort of been like Fox Mulder, this kind of Fox Mulder entity where I'm looking for the truth, you know, trying to go through and being skeptical and looking through all these things. And I've looked in a lot of places outside the box. And it's really the whole where I come from with, you know, yeah. Why are we talking about the physics and the aliens? Yeah, all right. Well, you know, this is the community of people that are trying to basically bridge our technology with that of an advanced, you know, alien civilization. That's the whole idea. That's where the connection is. And that's the whole idea behind it. The channel name that I have is Alien Scientists, and that sort of name I created for myself years ago when I was trying to approach these topics of, you know, advanced, you know, outside the box space and aliens, and as a scientist and really with science in mind and at the heart. So it's really been, that's the link there with the aliens, and I'm sorry for people that can't see it or understand it. And you know,
if we were trying to figure out what ghosts were, right, then we would be bridging that boundary. We would be, you know, trying to, you know, talk about ghost hunters with respect to Phoenix, but we're, you know, trying to figure that out. That's not really our point. Isn't to try to resurrect your soul. Our point is try to get you out into space to another planet. And there seems to be, like any court of law, viable witnesses that these things have been here. Now, whether or not you believe them, that's an entirely different question. But the evidence cannot be denied that there are profoundly many reports across time about this sort of stuff. So the idea is, well, instead of disregarding, we would want to approach it in a scientific way, which is don't disregard the evidence just because you don't like it. What you tend to do is say, where does this evidence make any sense? Where does it fit in? Is there a larger explanation, right? And pursue more evidence. So that's our whole point. That's the whole reason why, we really want to be involved in and with the alien community of people who believe that these things do exist, have existed, etc., because we believe that there might be evidence there. Just like Sherlock Holmes, right? Just like the whole Sherlock Holmes saga. Any good researcher is not going to abandon any evidence unless they can conclusively disprove it.
Right.
Okay.
And that's pretty much my approach that I take into a lot of these topics too, is that there are some things where I feel like I've conclusively disproven, although I'm always open to new evidence or always open to new ideas. And so here we got, I want to point out a couple more things. So yeah, on that sidetrack, that for that one comment about the link and why we're talking about aliens and mixing that and kind of turning a lot of people off and sacrificing our credibility in the process. But yeah, always keep an open mind. Yeah, it's again is that I personally wouldn't have gotten where I was today and met the people I've met if it weren't for my ability to keep an open mind to a lot of things. And again, not so open that my brain falls out, but open enough that I'm at least willing to seriously not like scoff and look the other way completely. It seems, someone has something they can teach you no matter what.
The bottom line is, even Galileo, all of these people, they all confronted the same thing in their time, which is, please don't talk about that. That's against religion. Please don't talk about that. That's against whatever the belief system was at the time. Einstein, please don't talk about that. That's against, Maxwell's equations, even though they work for it. But that's also against, our whole traditions of physics. That's what every layer encounters. So do you really want to be on that side of it? Or do you want to open your mind and say, hey, maybe there's something here? Okay? Science is nothing but the next step. So let's see if we can make those kinds of next steps. Sometimes they're leaps, okay? Leaps of faith and fact. But nevertheless, they're still steps.
So I got a couple comments from Tim Pickrell here. He says about Jim Woodward and then this white Jude warp field interferometer, the warp field interferometer, where he says the work at NASA seems to have produced a warp effect. And I have not heard of this yet, and it's new to me. Actually, I think I might have seen something about this before. Oh yeah, I saw this when I was getting picked. When I was actually used some of the pictures from this in my video. I found. Actually, I remember seeing this whole thing about that. Yeah. So, yeah, it's very interesting if this work that's being going on at NASA. And again, I don't believe we're the only ones doing this or that know about this. I mean, maybe we figured out a next step involved in this that we've put out with this new theory, which I really think is the crucial step in creating warp drive technology. There's a lot of interesting research that's being done into this, and literally people need to wake up, because within 2 years science fiction is going to be reality.
That's right.
You know, this especially this piece of science fiction, which is so long overdue at this point. It's really like, where has this been? It should have been here a long time ago. And
yes, right. And you know, from my own studies, the idea that that we have such technology, yeah, there's probably a good statement for that. However, what we're missing, and have been missing for quite some time, is just a good theory to understand why it works this way. That's really the missing element. I think that you can build a door without understanding necessarily what wood is, right? But you can chop it, you can sand it, you can do all sorts of stuff to it. And it will work as a functioning door, even if you don't fundamentally understand what the heck is going on. Okay, it just works. So I think that has been a tendency when we're talking about, you know, revolutionary technologies, is that generally it becomes the technology that we adopt when we begin to really understand how the heck is it working. How can we control it in the way we choose to control it, just by virtue of understanding how it works. That's the whole reason why the steam engine became the major, you know, form of transportation. It wasn't simply because, you know, people put steam out there and figured out how to crank a wheel with it. Figured that out. What people figured out in the days of Carnot, right, the Carnot cycle, is what they figured out is how to use that steam to the best result. How to gather as much energy from that steam as is allowable in the physical universe. And so that whole thing created the revolution of the steam engine. That's why we have a steam engine. That's why you could drive a train with it. And that's why with that train, you could pull tons and tons and tons and tons of things that you just could not do with a horse and buggy. So the perspective is that, you know, new technologies really are coming about really because we have an understanding, some understanding of the underlying physics, so that we can make it better. We can make it work in a way that works for us, you know. Same thing with, you know, bacteria, right? Well, bacteria have been around since we've been around, but only recently have we been able to understand how to get that bacteria to start doing radical things inside of the cell, like curing some form of cancer, right? That understanding is recent, because only recently have we understood how these bacteria work. And there's been a lot of science behind that. So that's what I'm saying.
No, and I agree. Question from Mr. Naruto Sapek. How long and how much money to get the first experiment done? Well, that's an interesting question, because right now it's really about we're really looking for lab partners and finding the lab to do this. If we can't find one, then of course we have to at least put our own together, and we have some facilities we're currently looking at for that, and some people that we're talking to have plasma lab and some access to some equipment. Of course, we're going to need to buy some additional equipment. It'd be nice if we, you know, had a partnership with the laboratory that had access to, you know, high-powered lasers and the type of equipment that we're going to need to do the first initial experiment. I'm guessing it could take anywhere from 3 months to a year to get that first initial experiment done, get the funding raised for that. We've already had quite a few investors and people who are interested who have inquired about this. And once we get the initial investment and platform set up so that people can put an investment into it and see that the money is going to be going towards experiments and towards this very definite laid out lab plan, that they will see that that money will come in very quickly, and that we can get that together and get that executed in a properly and in a time efficient manner, so that we can perform that initial experiment and show the results. If we can do this with that piece of silicate, again, we're going to take a uniform piece of silicate material or rock, and we're going to essentially fire lasers at it to create antimatter fields, and hopefully hope that those antimatter fields do what they do according to these theories, and that is break quantum entanglement and thereby reduce or negate the effect of gravity somehow on this, which we intend to then measure and then show those results, you know, of what we're able to achieve. And again, that could take anywhere from 3 months to a year, depending if, you know, tomorrow some laboratories could approach us and be like, look, we're going to give you, you know, free reign for a month to come here and start performing experiments, and we'll give you access to our labs as long as, you know, like, or whatever the arrangement is going to be. We'll have to, you know, obviously they're going to have to get something out of it, and we're going to have to get something out of it. And it's really what it's about at this point, is finding the right lab partners, the people that we can work with, the people who have the talent and knowledge to be effective working with us and getting this done. So it's really it depends on you. Depends on whoever's out there watching and listening, and whether they want to take a risk to get on board with something that could potentially prove revolutionary. So, yeah, it's hard to say what about the estimate what we need for monetary wise. What we're guessing the range of about for all these lasers, the plane tickets out there for us to go to the laboratory, the lab space, you know, paying off whoever to let us use their lab space and giving them some kind of thing in return. Yeah, probably around 150K would be a good estimate. We might be able to do it for less than that. It might be a little more than that, but yeah, a good ballpark range, I would say. Yeah, somewhere around there, just to get this initial experiment done. It's not that hard. These lasers, not super expensive. There is, of course, you know, the powering of those and the power supplies and systems that have to go into that, and then setting it up, and then of course the lab safety and getting it all done. And I already have the video camera and equipment for recording it and setting it all up, and then showing it off. And then it's about, you know, inviting others to come and check the results, and then showing other people how we did the experiment so that they can go and try the same exact thing and confirm. And then where do we go from there? Yeah, getting it published, and then filing off patents for, you know, technologies based on it that we can sell those or lease those patents to industry to pay back our investors, so that our investors get money back for what they invested. And the only way to do that is with business, you know, with selling something, making a product or something that we can sell. And we have a lot of ideas, and we've been thinking hard about those things as well, and what kind of products we can develop and what kind of products we can then sell and market to different industries that already exist and have a need for this type of technology that's going to be coming out. So that's pretty much where we're at. Yeah. What is can you make a video with some cool 3D visual effects and animation of Ken's Phoenix theories and particle interactions? Yes. Yeah, I've considered that. Me and Ken have talked about it, and making some new videos to basically show off some basic Phoenix and particle interactions and stuff, and showing that off a little more. Yeah, we thought about that. It would definitely be something in, you know, in the future, if it's in the time constraints and in the budget. So we'll definitely be doing some more educational outreach on this to break it down and explain it to people. Eventually, we're hoping that it would be a way that, you know, that physics is taught, so that people can learn, you know, particle physics in a way that's not so confusing and complicated. So that's eventually what we're hoping. What is the disk material? Yeah, it will be a silicate disk. It will be silicate, which is rock, in other words. Yeah. So no metals. There's a lot of different ways to float a piece of metal. A lot of different tricks that can be used to float a piece of metal. So we're going to make sure that we show that this is a rock, that it's not magnetic, and it doesn't, you know, have like a magnet hidden in it, and all the other tricks that people use to fake things. So yeah, it's going to be really something different, and we're going to show people how it gets done and how to replicate it on their own.
Replicate it.
So that's the important key to science, is that if you can't replicate it, it doesn't agree with the experiment that others can perform and replicate, then it's not real.
All right.
Get recognition.
That's how you know your card can work when you turn it on.
Right? Yeah. Elon Musk picked this up, and yeah, we're going to get a presentation together. We have a PowerPoint already put together that we can present for our investors. So we have that put together. We're thinking about other presentations just to present the theory and talk about the theory and some of the applications of it. Again, we were looking at TED, getting this presented at TED. I'd like to see Ken present his theory at TED, actually. I think that would be amazing. But the thing with TED is you can't promote your business or ask for donations or money or any of that stuff. So we'd have to leave the HoverBrothers part out of it for now, at least, and just talk about ideas and this idea of using a new theory of particle physics and that what that new theory is and how to use it to create warp drives and the antimatter required to build those warp drives. So the negative energy states component, which is antimatter, according to this theory. So, yeah, I would love to reach out to some of these other conferences. I'd like to be invited or to get connected with other conferences so that we can plan a big part of 2018, I think, and I really believe is going to be us reaching out and spreading information and ideas about this and doing the conference circuit and podcast circuit to talk to more people about these ideas and get the message spread and out there in a way that people can really eat up and not be so, confused or turned off by or get these mixed messages that I see in the comments as I go through on that video, seeing the people that it's just outside their comfort zone of what they want. Yeah, TED would be great if we could get on TED Talks and get this presented there. Again, the whole reason that we're asking for money and doing this donation thing that's turned so many people off that they said, oh, this is just an advertisement, it's a fraud, it's just a hoax, it's a big scam to make money and stuff. And if you worked for 20 years of your life at something, wouldn't you want to be compensated in some way for it? I could have had a career in physics and gone out and done a lot of other things in my life and try to get information for random strangers on the internet and publish this stuff freely without really, I don't make a lot of money on it. I could have done a lot of other things. I could have probably had a lot more to show for it in life now if I had chosen a different path. But unfortunately I didn't, and I'm here, and Ken's here, and it's the reality of it. With Tesla, you look at the conditions that some of these other people came from. It's no different. It's literally, we're just trying to make sure that we can get something out of this for all of our hard work back.
That's right.
And that we don't end up like Tesla, we're having it all stolen from us, and that we end up penniless, and starving. That the last picture of Tesla ever taken, you've seen how he looks, man. I don't want to end up like that. Sorry. That would suck.
As Nikola Tesla came into Tycho DeVry's presence. Well, Tycho had money, right? But if when Kepler came into Tycho's influence, Tycho had money. Tycho was able to take care of his living needs while, guess what they discovered? They discovered that the orbit of Mars was not a perfect circle. That's what they discovered. And that discovery led the way to what Newton was able to perform and say, this is why we know gravity is gravity, and these are the equations that describe planetary motion, simply because Mars had an eccentric orbit.
Yes.
Only came about before Kepler, had a chance to actually work with somebody who had a little bit of money to keep him alive while they performed the research. Scientists don't ask for a lot. They really, really don't. But they don't get a lot either. Let's be honest about that. Right? So the profession of going into astronomy or going into physics, or going into ufology, or going into any of these sorts of things, basically takes you, your life, your soul, and your family, you know, to be able to get you through that. It's not easy, and although, you know, we have rewards, you know, when people look at us and we're like, okay, was it really worth that? I mean, look at you, was it really worth that? And we have to keep saying, yes, yes, I might not be able to see that future, but yes, it was worth it. Sorry.
Yep, no, I agree. So I'm going to answer a couple more questions, and then I think we're going to finish this off and end it for the night. And I thank you all for joining and all the great questions that you asked, and all your support and interest in this. Here was one. I've arrived late, so I'll watch this through afterwards. Have you come across the emergence theory from the quantum gravity research team? And if so, do you have a thought towards it as to that scale on what information is? And I think, I just watched the whole quantum gravity research team's presentation there on their video and their description of what they're doing. There's a couple interesting points from that I wanted to relate to and also sort of clarify. One was this whole idea of that every point in time is infinitely connected to every other point in time, that we're influencing ourselves through the past and through the future, and that this sort of notion of time is all connected. And yes, through quantum entanglement, time is connected temporally, but in a different way than they're sort of presenting there. It's as if light is bouncing off and creating this illusion, or creating this hologram of the universe through photonic interactions, and that those photons are all essentially almost the same photon. They're almost the same energy and the same thing, right? Am I getting that correct, Ken? That we've said that yes. It's almost like this single thread of string, but it's bouncing around at different times in different places. So it's temporally, it's disconnected to all these different points in time, but it's literally part of this same dynamic that is all going on constantly. It's a very interesting, some very interesting philosophical points that they alluded to and came to in that discussion. And I think that again, we pointed this out before, but their approach is this sort of top-down approach, is that they're looking at these symmetry groups and these applying these, the E8 Lie group to this quasi-crystal, and then applying these symmetries where they can see where they line up, where the vertices line up, and that's where the particles lie. It's top-down approach, whereas Phoenix is this bottom-up approach. It's looking at the vertices themselves. That information sits on those vertices in the form of these spatially entangled states of energy. And that matter itself is energy that's just trapped or entangled, and has this information value property to it, and about in the effect of how it's trapped or sits on those vertices. And that information about the particle there shows how that particle interacts, and so on and so forth through Phoenix. So again, we went over this earlier, and I encourage you to go back and watch that. Have you considered starting a crypto ICO? Yes, we talked about that already. I know it could pull in tons of cash really fast, but the problem is I don't know how to set that thing up myself, and if I have someone else do it, it could pull in tons of cash for them really fast, and then people would be asking me, oh, what happened to all the money? I lost it. No, I'm not going to do that, and ICOs are a very volatile market. I wouldn't be basing it completely in Bitcoin, as some people have suggested, or tying my entire investment to a single currency that is very volatile and could jump up or down at any point, or completely collapse. So I don't know. I had a lot of high hopes for Bitcoin and the way it was sold to me and the way people have described it, but just looking at it and how it's functioning and what's going on with it, it's just not there yet, or whatever is going on with it. So yeah, it's still got a way to go. dying to see what I'm dying to see what we can come up with too, man. Once we get the right lab setups and the right people connected, I cannot wait to see what we do and what we show. Again, it's literally, there's no better time to be alive than you could have ever been born into. I mean, Tesla lived in a great time where he took some emerging theories of electromagnetism and was able to apply those to create a series of inventions which completely changed the world. He lived in that time period where he had the insight to see that, you know, hey, these things don't exist yet, but I can see them, and they're clear as day to me. And he just needed to be able to someone who could take that technology, that theory, and then apply it and use it to create these inventions and build the world that we see today. The electrical AC electric grid and infrastructure that your computer is running on right now, that you're probably watching this on or talking to me on. So again, we want to do the same thing. I don't know, don't get them started in cryptos and blah, blah, blah. Yeah, cryptos. What is the scaling of the device? More power, more lift, or does it require multiple modules to produce a working device? Again, there's different levels of this warp drive. The first one we're going to create is just that proof of concept. It's just that initial test to show, yeah, we can float a silicate by creating warp fog or warp foam. It's not a controlled warp bubble or a warp, this definitive warp field. It's very low level warp. It's the basic experiment that we need to show to basically show, like, oh, well, there's an effect here. It's reducing the mass of this object slightly, and now you can try to explain it. And and of course that goes from there about how do you explain these effects, and then how do you scale them up and create the real deal technology like that we're after is actually turning that low scale experiment into the next step. And
let me kind of like this, because you're exactly right. Another metaphor to you could be like, we're creating the first incoherent light source, meaning that we've got wavelengths all over the place. So we're proof of concept that light exists. We're creating the first light source, but we already know, if that's true, we already know how to create a laser beam. So we're just waiting for the "if that's true" part to be measurably demonstrated. That is, that our light source, this incoherent flood of white light, can actually be this. But we already know that if that's true, we know exactly how to create a laser beam, which is a coherent beam of light of a singular frequency. That's where warp bubbles, that's where that warp technology is found, in the coherent beam of light, or in the coherent demonstration. But that this is just a proof of concept that all the other stuff is really on target and true. But then we can go to the next step.
Yep, I agree, and it needs to start somewhere. And this theory is an excellent start. We have that missing piece that all these other warp drive theorists and people talking about building warp drives and dreaming of warp drives we're looking for. And it really is going to be astonishing to see what is actually going to happen and come out of this over the next 2 years, and what the future holds. So again, thank you all for joining with us and bringing the great questions that we've had so far. Again, I'm going to try and hold more of these in the future once we have more updates and things to show. We're going to be having some meetings next week and over the next couple of weeks to go over all the investment stuff and and also to talk to some laboratory people. I had a comment here. Yes, email us if you have labs or access to labs and you want to help us out with this. We would love to talk about collaborations with Ames or one of these big scale laboratories. That would be amazing if we could get in a room at one of these places for a month and tinker around and get the equipment we want and do what we want to do. Because I have a feeling that we could push this technology bubble the step forward that it needs to really go at this point. So thank you all for joining in and asking some great questions, and I can't wait to help bring this into reality with you all. Really, that's we're doing this.
That's right. That's exactly right. So thank you guys.
All right, take care.
Yeah. See you next week.
May the force be with you.
That's right. I was with you.
All right, guys, take care.